We are going to talk about observability, and we're going to see how mulog fits into the picture. So Clojure talk is a mandatory definition. So the one I found that best represent what I want to say is this from Wikipedia says, in control theory, the observability is a measure of how well internal state of a system can be inferred from knowledge of its external output. So you have a system which is like a black box somewhere in your infrastructure, and you want to infer what is the internal state, because you can't understand directly, you can't observe the internal state directly. So you use a sum of its output to actually infer what's happening inside. And there is another note there that said, for the concept in quantum mechanics, see observable. So if I go and check down and say, in physics, an observable is a physical quantity that can be measured. This is also important. Sometimes we want to measure things like the temperature or some other physical measure of a system. So I think these two are probably the closest definition of observability, which makes sense in the context I'm going to refer to. So for more than a decade, I've been building applications with big distributed systems, and I typically also operate the system I build. So I go with the motto, no, you build it, you run it. And one of the habits I took during this time is that every morning before I read all the emails, I sit down with a cup of coffee and I go through the dashboard. And I look all the main dashboard of the key systems to see if there is anything wrong. And it is amazing to see how the brain evolves and starts to notice patterns and anomalies. Even I don't mean that things now, the squiggly line it was in one way and now it's different, but things more deeper in the system that you start noticing the system, even if it is everything fine, you see when it starts behaving differently. And this habit is something I took, I built on, and I think it's a really good way to have a close feeling with a running system. So when I join typically a new team or work on a new project, I ask the team to take me through their system. So they show me the code base, they show me the documentation, they show me all the system that they have. And inevitably, we get to the point that they show me this beautiful dashboard. Right? In some places, the screen with the dashboard for the system, it looks like the NASA control center. It's really amazing stuff. And sometimes I get closer to one of these graph, and I look there and I ask, is this request per second or request per minute? And then inevitably there is like a big silence. I turn around and the person is looking at me this way. It's like he has no clue. So this is the product he is building. Is the thing that he should care about, is running every day. He has no clue what all this dashboard means. So at that point, I think it wouldn't be better just to have, instead of having 1,000 different metrics, 1,000 different graphs, having just 3-4 key metrics that you observe about the system. And you try to understand, give you a good overview of whether the system is good or not. Many people would argue that this is not possible because the systems are too complex. There is memory, there is a CPU, there is temperature, there is IOPS, there is the disk space. There's so many different things that they can go wrong. You have to measure all these things. Yes, I do agree. You have to measure all these things. But I'm pretty sure you guys are familiar with the bedside monitor that you have in the hospital. Now, if you look at them, those ones, they only display 3, 4, 5 different measures. There is temperature, pulse, and all these things, heart rate. I would argue that a body is a kind of complex system, and it's got hundreds of components, and each component can have, tens or even thousands of different type of measure that you can observe. So why doctors, they decided to have only this key metrics? I think it's because nothing can happen macroscopically to the body with that. Something will happen to the body that it won't be reflected in any of these metrics. So the idea is like those ones, they are the kind of the filter for everything else. They are the fundamental metrics. And I believe that it is possible to do the same even if we software systems. So there is a number of fundamental metrics, and those metrics, they are such metrics that nothing can happen serious to your system that you can't observe through those metrics. So one of these is the request rate. The request rate is the number of requests processed in the unit of time. And you can decide what is the unit of time. Or if you are not, if your system is not a system that does request response, and you have a system that processes items, then is the number of items processed in the unit of time. The other one is the error rate. So you want to know, out of these items that you process, how many they were successful and how many they failed. And why it's important to have both? Because if you just observe the error rate and you get zero, there is no errors, maybe it could be that your system actually gets also zero requests. So in that case, you have maybe some problem upstream that the traffic is not getting to your system. So if you just observe the error rate, you would think that your system is all fine, while in reality, it's not getting the traffic at all. So both together, they give the best overview of what's happening in the system. And by observing how these values, they change over time, you can get a very good understanding of how your system is behaving. Interesting as well is the latency. So how long it takes the system to process a item or a request. And here, you don't want to just capture the average value. It's more interesting to capture the entire distribution. And we're going to see here why it is important to have the distribution. Now, the last one is the saturation. The saturation is defined as the percentage of the system which is currently in use for processing the request in the system. So this can be easily calculated with the Little's law. But I would argue that this one is not really a fundamental one. Now, if you discard this one, you don't consider the saturation, your system goes over the saturation, over the 100%, so something is going to be reflected in the latency or probably also in the error rate. So I would argue that probably the first three are really the true fundamental one. So one of the charts that you should have in your system, it will be something like this. It will be the volume or the rate of requests displayed over time. So on one axis you have the time, on the other one you have the rate of number of requests over the unit of time. In this case, it's seconds, and it is important to put always the unit on the axis. And you can see that the shape, it will go up and down. It will during the day or during the week, depending on the traffic. So it is also interesting to see the errors at the bottom. Most of the time, it will be in a real high volume system. It's almost impossible to get the errors down to zero. There is like always a number of errors that will always pop up. That most of them, they depend by the user, on the user, and on some changes in the infrastructure. Now, if you watch this every day, you can get a feeling of when the system is actually operating good. And sometimes you can compare the same graph to the what's happening 1 week ago or 1 month ago if there is a certain cycle or seasonality on your application. So you could check whether the number of requests last week, the same day, same time, it was any different from this and graph on the same chart. Some people prefer to have the error on a different axis. If the disparity is too big, the errors will be almost flat on most of the time. It would be not so easy to see. So what if one day you sit on your desk with a cup of coffee and while you're going through, you see this? What happened here? What happened here? Now, if you just capture the number in terms of errors over time, of a window of time, it's very hard to understand what happened here. Now, you need to have a context. You need to have what happened before and after this, if there is any change. And maybe the change was that you decided to, or somebody else decided to deploy a new version. As the version is scaling down and the new version is scaling up, you can see a different amount of errors. But without the context, it's pretty much impossible to understand what's happening just by the number. Now, there is most of the new last few years products like do matrices, they like InfluxDB or Prometheus, they also account for labels or tags. But I would say that this is far from enough, and I will show why. So what if you wanted to understand what this anomaly is? No? How could you say, just by tracking the number of requests? How could you see it's maybe a new client that uploaded something, a number of hundreds of thousands of requests in a short time? Maybe it was someone abusing the API. Maybe it's someone batch loading something. Now, how would you know without context? No. Here again, the lack of information, the lack of context here is the problem. Latency distribution. So we said that it's important to try to trace the latency and to have the full distribution. So we can see here, so this beautifully hand-drawn distribution. We have the median, which says that half of the requests, they are 7 milliseconds or less. Typically, on a performance-related distribution, there is always a minimum. And beyond the minimum, it is not possible. So less than 3 milliseconds in this case, there is it's not possible to have requests, because this is the minimum physical time to get the request processed. But as you can see, the graph is not symmetric. On the right side, the time is unbounded. There is a huge amount of things that can go wrong and delay in the request. So that's why it's important to track what is the long tail. So this is a gamma distribution, and it's very different from the normal distribution that we study in statistics. So all the math that we know about the normal distribution cannot be applied here. The gamma distribution have a completely different set of properties. More than so you can capture this distribution at a given point on time, but you can also trace it and see how the distribution changes over time. So in this case, we plot just the median and 99 percentile, and it could be 99.9 percentile or 95 percentile, depends on the measure that you care about in USLA. What if you go one day, you use this? So you have your 99 percentile that went up by a certain amount, and your median is pretty much the same. So this is much different, much more difficult to understand, rather than if the median as well went up, because the median going up, it means that pretty much all the requests are slowed down. In this one, it means that a small portion of requests, they get slower. So how those requests are different from the other ones. So what I really would like to do is to be able to select an area where the things were okay, an area where the things that were not okay, and then have a diff. And have a diff that returns me in which way the requests that were significantly, in which dimension they were significantly different. No, what is the difference in the request that we can account for this change in the duration, in the 99 percentile. And some of the products there, the closed source products like Lightstep and other companies, they are starting doing offering this type of things. But I think as long as these properties and this information is close in certain proprietary products, we're never going to leave the middle age of observability. So at this point, for me, it was clear what is the problem. The problem is that I need to have much more context in the metrics and in the logs I send to the observability system. I need to be able to understand, have the full data to be able to actually detect this type of things. So it was clear to me that I was going to solve, if I was going to solve this problem, I needed a completely different tool. So my name is Bruno Bonacci, and this is mulog and the next 100 login systems. So if you Google about observability, you pretty much end up in a page with this picture here with a few clicks. The article talks about the pillars of observability, and he described this like with the design of this temple to give some sort of classical importance to the what is about to say. And the idea is that something happening in your system, and every event is like a snowflake. It's got a number of dimensions, and this event is unique from everything else. But what the metrics are going to do is they're going to just take account of the event. The traces, they're going to just take some measure of the relation between this event and other events within the system. And the logs, they're going to just send some random data. And I would suggest to enable you guys to enable the debug loggings into libraries that you have in your system to see how useless those logs are. You get things like, I open this, I close that, and how this is useful information. What does it tell me about the system? It only tells information to maybe the developers that did the system, and nothing else. Is no useful information. So the observer is here on the top, and in this idealistic world, it should be able to infer. Now, you remember what we said about the definition of observability. So the user from the top, he should be able to infer the state of the system by this fragmented information. So the different approach that mulogs take is that instead of fragmenting the knowledge about the event, mulog wants to capture exactly the event as it is and distribute it to all the systems, instead of just taking some of the aspects of the system. So what you end up with this traditional approach is that when you look, your temple looks more like this, looks like a ruin. So from the event that you wanted to observe, a number of important dimensions have been arbitrarily taken away by the very same tooling that was meant to help you to observe the event. So the tooling that is meant to help me to observe, he arbitrarily removed some information. I didn't tell him. Because they work in a very prescriptive way, so they decided that this information was not fitting in their model, so let's discard it. So it was clear for me that I needed a tool which it would capture the event in its true form, without forcing formats, without imposing constraints, without losing important details. So that's why I built mulog. And what is mulog? Is essentially a data capture facility. So it is a high fidelity data capture. It does not impose a scheme or a structure. It doesn't limit on what you can capture, and it does not impose a format. So it lets you capture the events as pure data, and you can process as a pure data. So that's why also I'm struggling to call mulog a structured logging library, because there is no structure. You just capture the events as you want, and the service it provides is that it collects the information and it ships the information to another system. And then what you want to do with the data in that system is up to you. So let's see why I built mulog. So the things that provides value for me is the application. Obviously, it's the things that pays the bills, and the things that the people pays me for. But to run a successful app, you need the monitoring, you need alerting to make sure, like the bedside monitoring system, you need to make sure that your patient is alive and you can keep serving requests. Sometimes you need the APM tools, application performance management tools. Sometimes you need to verify or check security concerns, auditing, and sometimes you can use machine learning for insights. But essentially what an application does, it performs a number of important operations. So if I want to create an order, the order is going to be sent to the fulfillment service. It's going to be created on the database, and I'm going to send an email to the user for notifying that his order has been accepted, and so on. So there is a number of key operations in the system that they are really important. Because they're important operations, then I wrote a library years ago that is called Safely. Safely wraps is basically all the code I've wrote for the last decade. It wraps all this important point inside the code. So when there is an operation, the operation is wrapped by Safely. And Safely, what it does is a circuit breaker, and it's got a declarative approach to retries. So you could say, try to write this, send this request to the fulfillment service, and if it fails, retry 3 times with exponential backoff. And you can say this declaratively, there is circuit breaker to apply, there is a ton of configuration that you can apply. Because this wraps all the important operation, I want to know about these things. So there is logging and metering information that comes directly out of the library. But in the past, I used the Coda-Ale matrix library, and I wrote a Clojure wrapper for it called Trackit. And that library used a typical approach that you can count things and have a gauge meter, counters, and all these type of things. And I was always unsatisfied with the level of details, because as we've seen, I need more context. I want to know, so when my request was successful, how many times it's been retried before? So how long it took every single attempt? What was the total time? And all this information. And all this information, they are not available just with the traditional logging. So the idea came out for me to build a library called mutrace. Mutrace, it takes a code block and it tells you important information like, was it successful or there was an exception inside? What was the duration of the execution? So how long it took to reach the database? And it adds all the capability, all the information around the context that I'm using at the moment. But to build the mutrace, it was clear to me that I needed something that to actually collect and ship this data reliably. And so I built mulog. And then I realized that when I was designing these things, that 99% of mutrace is actually mulog. So now the two libraries, they actually merge together. And this is the name of the two main macros inside the library. So essentially, mulog is just a facility to collect and reliably ship the data to downstream systems. And there is no constraint on how the data looks like. In mutrace, it traces the execution of the code and the relationship between other code blocks execution. And we're going to see more of what does it mean. So what is the typical setup? The typical setup of an application which is not using mulog is this. If you're running on Kubernetes, you have your container running in a pod, and the pod output the stuff on the standard outputs, and then we have log rotate and an agent grabbing the output file and send it to Logstash. So this is one of the possible solutions of the Kubernetes configuration. I took this picture directly from the website. So when you reach Logstash is basically has to invert what the application did. So you had an event on your application. You had to convert this into a message that you're going to print on the standard output. And now you want to do the opposite. In Logstash, you want to grab out of the message what is the important information that were sent into the log line. So then you use regular expression configuration, and then the information is sent to Elasticsearch. And Elasticsearch, then you can query Wikibana and visualize all these things. Now, here for me, it was madness that in the application, I have full-fledged objects, values, maps, and all these things. And I have to represent this as a message because my login system only allows me to send a message. And then the message needs to be decoded on the way up before you index with Elasticsearch. This was madness for me. And I also on mulog, you have a different approach. On mulog, you connect directly to Elasticsearch. The data is sent directly to Elasticsearch, no middleware, no necessary of Logstash. And then you can query directly with Kibana. Now, I cannot stress how Elasticsearch is like amazing for this. I never used Elasticsearch, or I barely used Elasticsearch for logging management. I mostly used Elasticsearch for analytics, and I can assure you, Elasticsearch is really, really good to count and aggregate and do this type of operation across a huge amount of data, slicing and dicing the data very easily. I can tell a story. A few years ago, I was working for a UK television broadcaster, a top UK broadcaster, and they were using EMR and AWS and Hive on top of EMR to do SQL query on top of large data sets. We're talking about terabytes and terabytes of data. And I was working for the research and development, so I built like an Elasticsearch cluster to compare the performance. Now, comparing the performance between the Elasticsearch cluster and EMR is kind of difficult because the architecture of these two things is completely different. So what I did was like to compare them on the cost per hour. So the data analysts, they were running a cluster of 10, 15 machines to run a bunch of queries. And this cluster, they had a cost. So I built a cluster of Elasticsearch that had a similar cost of the query clusters and indexed the same data. So I remember we did some performance comparison, and a query that's on EMR plus Hive, they were taking 2 hours and plus to run. In Elasticsearch, we're taking only 6 seconds. 6 seconds, it will build also the picture within all this time. And this, we're talking about 1.8 billion rows. So it's not just a little data. And at the time, it was not even running the cluster on SSDs. It was running on a normal spinning disk. So I feel that Elasticsearch is one of the underappreciated piece of software in our industry. It's really amazing tool. If you ever worked with a Elasticsearch cluster and the performance is sluggish, I can assure you is because the setup is not done properly. So Elasticsearch is like an amazing tool to slice and dice the data, but you need something to visualize the traces and the relationship within the data. So you can just plug something like Zipkin out of the same data that you get out of mulog, and now you can see the relationship between your code blocks inside your code. You don't have to add any other tool, any other instrumentation, just mulog. Now, it happens also that you might want to send your data to Kafka, to Kinesis, and have the normal streaming processing application processing this data. You could use like a Kafka Streams or Storm to do your computation. You can do analysis. You can create a dashboard in real time with all these tools. You could just send it to S3 and then use AWS Athena QuickSight to run select queries on top of your data. And now we know the Elasticsearch cluster, especially if the volumes are really big, so it starts to cost a little bit. So you can actually have, like, for the last few weeks, Elasticsearch, and then all historical data on Athena, and then you can use a select statement to query your logs. You can send the exact same data to CloudWatch. You can use CloudWatch to auto-scale your system. Now you don't need an external measure of your system like CPU to scale. You can scale based on internal knowledge of your application. How big is the queue inside your system? How big are the items to process? And you can use this information to push it to CloudWatch and then auto-scale your system with that. You can send it to Prometheus, and because people use Prometheus with PagerDuty, you can get your PagerDuty to send you information. But personally, I don't like much Prometheus. I don't think it's like a good approach. If you actually use Elasticsearch properly, you completely forget about Grafana and Prometheus. So we talk about the motivation. We talk about the typical setup. Now, how does a mulog event look like? So in this part, I'm going to go through the library and how to use the library. And then at the end, we're going to see what's coming next. So in the line number 1, it will be what you add in your code. It will be a call to mulog. And then there is an event name. It's typically a keyword, a namespaced keyword, but it could be anything. And there is no imposition there. So mulog automatically adds a number of information. So that you have the timestamp of when the log line was called, you have the namespace from where it was called, and then you have a trace ID. A trace ID is like a unique identifier of that particular event. So it is a flake, like a snowflake, because there is no two snowflakes, they are the same. This is like a 192 bits time ordered monotonic unique identifier, which I built in the mulog library. So there is 64 bits which are based on the monotonic time, and 128 bits that are purely random. Just for comparison, the UID only has 122 bits random, 6 are reserved. So there is more. Definitely you don't have to worry about collision in this. And then as a final things, there is key value pairs. The information, this is the information that you want to send to the external system to make your events more meaningful when you query. This information is just collected and sent away. There is no transformation. There is no restriction or things like that. Only there is obviously don't use values, don't use objects or mutable data, because the capture time and the send times are done in different threads. We're going to see this later. So you do definitely don't want to use mutable data there. Apart from this, you can put as many as you want. You can put whatever you want. mulog is going to just grab it and send it to the target system. And then you do whatever you want in the target system or with the data that you send. So let's see now how the trace look like. So in the 1 to 4, the line, you have the trace. The trace is, again, similar to before. You have the name of the events, followed by a list of pairs, key value pairs that you want to add to the event. And then there is a code block, which is typically an operation. So this operation is something important that you want to trace. Like we said, it's gonna he adds a number of ID. You have the trace ID, the root trace, and there is a third one, which is the parent trace. And those ones are used to capture the relation between the trace events. And we're gonna see how this is gonna be used later. So there is a duration captured in nanoseconds. So this is like the duration of the block, and it's captured with a high fidelity. And then you want to know whether the operation was successful or there was an exception. If there is an exception, the error is added there as well. Otherwise, the key value pair that you add, they get added as well in the event, and then you do whatever you want with that. So this is like the underpinning of mulog, or how the data looks like. Now let's see how to use the library. Sorry. So, application idea. You take a selfie and you upload the selfie, and the service generated dancing Santa with your face. If there are many people in the picture, it generates one or more Santa with every person in the picture. So let's say that we want to use mulog on this fictitious application. So you require the namespace, and then you set the global context. This is advisable, it's not mandatory, but it's good things to do. So in the global context, you can set, for instance, things like the application name, the version, which in this case is taken from the resource bundle, and the environment is something that, depending on whether you're in production on UAT or dev, the cluster is going to tell you where are you running. So the idea here is that the information that you put in the global context is information that is valid for every single event sent in this system. So any call to mulog or mutrace after this call will inherit those key value pairs. Obviously, you're not limited to these three. You can put as many as you want. You can put the OS speed, the Java version, the host, localhost IP, the AWS region, whatever it is significant for your application. Then you have to determine where you want the data to be sent. So there is like for development purpose, there is a console publisher, and it returns a function, which when you call the function without parameters, it just stops the publisher. But most of the time, you want to send the data in multiple places. So there is a special publisher called the multi-publisher, where you can provide a number of different configurations. So in this case, on the line number 7, we send to the console. On line number 8, we send the same data to the file on the first system. And 9, we send the same data on an Elasticsearch cluster. So this is the same data that gets distributed to all the destinations. And adding more publisher will not influence how long it takes to execute mulog or mutrace, because they are completely separated um, different threads, and we'll see this later on. So running a mulog statement, it takes around 300 nanoseconds, and whether you have 1 or 100 publisher, it does not affect this. Next thing you want to do is give an information that your application is started. So this is, it seems silly, but it is quite interesting to see, especially now that there is all this container management system. You would not imagine how many people have no idea that their application is crashing and is getting restarted, because Kubernetes is really good on restarting the application somewhere else. Most of the people don't even know that the application dies multiple times per day. So add just this statement. On this, with this statement, you get mulog event that tells you the event name is upstarted, plus all the information that you put in the global context. Those ones, they get attached as well. As we said, they will be attached on every single event that is executed by this JVM. How do you use mulog? Simply, you do an operation and you say mulog, something happened, and then the key value pairs that you want to capture. And you can capture also failures or exceptions, something failed. And there is the convention is that you put the exception with a keyword called exception. So that it's not a convention, it's not mandatory. So that when you query then the system, you can say, show me all the errors. You can just say, give me anything that's got an exception. And that's pretty much how you use it. So we said the exception get captured. So let's assume that we add an event called mulog order received. In this mulog order received, we get the order ID, which we want to pass. We want to know how many people there is in the picture. So there is a function that returns how many people there were detected in the image. We add the remote address, so the source address that send the request, and we can do a geolookup on the location. Now, with this simple information, we can already have an array of very interesting queries. We can see how many orders we get, order per second, order per minute, and so on. We can see what is the average number of people, or if there is any outlier, like big groups. We could use this information of, if there is one picture with 100 people, we could automatically spin up more compute power, because it's going to presumably take more time and more power to render 100 dancing Santas than compared to one. With the source IP and the geolocation, we can see if there is any particular region or city that is particularly used in our application, and if there is one particular address that is abused in our system. Already with this simple information, we can get so many out of it, so much information out of it. Now we have one function that renders the video. We get the faces, we get the Santa video, and it just does its job. It replaces the Santa face with your face, with each face, and then it outputs the video. So this is an important operation. I would like to know how long it takes. So I can wrap it in a mutrace and say, this is the number of people that were rendered. This is a video render event. And it's going to tell me if it was successful, if it failed, well, why did it fail, and how long it took. Now, assuming I have two other functions, I have one that once the video is rendered, he copies the video to the CDN, and finally I send an email notification to the user. And we'll assume that also those functions have been instrumented with the mutrace. So the overall order processing will look like this. I have a mutrace that say order processed, and then I say, okay, extract the faces, render the video, copy to the CDN, and send email notification. Now, if you remember well, we had also instrumented the render video, we instrumented the copy to CDN and send email notification. So there is inside those functions, there is a mutrace call as well. So it would be nice that the order ID, it gets attached to all the, even the internal information. So what we can do, we can add the with context and or another key value pair. So this key value pairs, like the global context, it gets propagated to all the events inside of this lexical scope. So the mu trace and mu log inside those functions inside the render video will also have this key value pair. So now we are done. If you remember the structure of the function calls, it looked like this. You run order process, the order process will execute the video, rendered, and then you have an asset uploaded to the CDN. And once that one is complete, you send the email. Now, if I wanted to visualize this with mulog, I can just use an OpenZipkin compatible solution like Jagger, and I can visualize the relationship between these calls. So you can see at the bottom, you have the order processed event that is the entirety of the order processing. And then there is the video rendered, which took 830 milliseconds. Then the copy to the CDN, so the asset upload, which is 380 milliseconds. And finally, you have the email sent. And you can see the relation between these things. And if it fails, you can see that it was a failure. You can inspect the errors and so on. So this is what I wanted, the contextual information inside the mu trace. And if you're using Zipkin, then it's just a different UI, but it's pretty much the same. So here there is like 20 plus calls executed one after the other one. You can see which one take long, which one take less. And on the right side, you can see all the other information that you put in the events. So you can see this is like the demo application inside the mulog. So this is pretty much how you use it. Now, there is one key feature that I think is worth it also to mention. Every publisher is got a free form, supports a free form transformation. So you can pass a free transformation to the events that they are going to a specific publisher. And the transformation is just a function that takes events, return events. You can do whatever you want. How can you use this? Well, you could, for instance, select different subset of the event and send them in different locations. For instance, I have in this case 2 different publishers. Both of them, they publish to the file system. One gets every event. The second one, it gets only the errors. And you can see in line 8 and 9, you have this transform, which is a partial filter exception. So it's going to filter only the events which contain an exception. Now, another possibility could be now that you want to send to Prometheus or to Elasticsearch or to CloudWatch only specific events. So in this case, here I'm using another library of mine, which is open source, called Where. In this library, it's just a library that creates predicates, predicate functions. They are just easier to read. So in this case, you can say filter where mulog event name is one of event 1, event 2, and things like that. But there is, it's got a huge number of predicate function that can be written in a much clearer way. So if you have a look to the libraries, it's quite interesting. But the point is, so you can use this to selectively send only the stuff that you're interested into. And because you are in full control of the data that you send, you can even transform. You can do whatever you want. So you can take a list of events. Let's say you have a third-party Elasticsearch cluster. You do want to send personal data to this system. You can just anonymize or just remove the personal information. So all the built-in publisher, they support this transform. Now, Let's see a little bit about the internals, and then we wrap up. So the mulog, everything starts when mulog is called. Mutrace just call internally mulog as well, so it's basically the same. So at the time you call mulog, the event is just captured as it is and put into a ring buffer. There is a timer, then every X milliseconds, you grab the content of the ring buffer. So this is like a staging area. As soon as data is grabbed there, and then the control is returned to the caller. So mulogs is very, very fast. It's just like under 300 nanoseconds. Once the event is captured into the first ring buffer, a timer then dispatches to all registered publishers. So here, if you have registered 1 or 10, the data is going to be just copied from one buffer to another to the inbox of the publisher. And for the publisher, you have an agent that wraps the buffer. So the agent is going to queue, and he executes one of two operations. One operation could be there is new events coming, so he's going to take the events incoming from the first buffer and add it to the local buffer, the buffer for the publisher. But the second request is a request to publish, which is controlled by the system. So the publisher is going to, a regular interval, take everything is inside of the buffer and attempt to post to the target system. If it is successful, then it removes from the buffer. If it's not successful, it keeps on the buffer, and it will retry after a configurable amount of time. So with most of the applications, most of the login system today, they give pretty much no help for writing robust delivery mechanism, and it's no easy at all. I can tell you that I had one case in one of the previous clients in which we had a down partition on the network for the system that was collecting the logs for many hours. It was over a weekend, so it took a few longer than usual. And all the applications that were not using mulog, they had some sort of problem. Some of them they ran out of memory. Some of them they froze. They kind of end up into a deadlock. Some of them they end up in GC poses that pretty much were freezing the application and or crash for out of memory. All the applications that were using mulog, they just worked as normal. There was no perceivable issue. Once the partition was fixed and the system were online again, mulog just sent all the data that was buffered while the system was down. So without losing pretty much anything. And without needing for human intervention to go and restart the system and plug the things, just once the partition was resolved, he just flushed the buffer and all the data was there. So this is like many other systems around metering. They have a different approach. They have like a fire forget approach. This is very different. We care about data. So we want mulog does everything is possible to actually capture and send the data before giving up. Obviously, at certain point, if the buffer is full and the system keeps on not being available, mulog has to decide whether to crash the application or just to drop the older logs. And I took the decision to, by using the ring buffer, to actually drop the older events. This gives quite a good reliability and robustness to the system, so that you can rely that the login system is not going to stop you from accepting orders. So one of the questions I get very often is, can I use mulogs with my existing login system? And so The short answer is yes. So there is this library made by Petabyte, which he made a backend for SLF4J. So you can use this backend to send all your existing logs to mulog, or via mulog, I would say. But I would say if the old logs, they are built with the approach that the human is going to be looking at this logs. So what I would say is, like, when you started logging with mulog, you should think, what if no human will ever consume these logs directly? So if you, how would you design your logs if only machine will consume these logs? That's the right way to approach the logs. So if you just try to activate the logs in your libraries, in like libraries that you find on the internet, like HTTP client or any other one, even popular one, you're gonna see there is a ton of useless stuff there. You don't want to have all the useless stuff sent to you. You can still filter. You can just send the stuff that you want. But I would say, no, use this library if you have already invested a lot of time and effort to make your logs of high quality and really good. Or if you want to capture events which are in deep down on some libraries which you don't have access, you can then still use this approach. Otherwise, I would encourage to design the logs, the events tracking in the way I said, that like if no human would ever consume this directly, and only a machine will consume these logs. So now wrapping up, going to the end. So what's coming next? So at the beginning, we saw a number of problems. Those problems, I want to be able to solve them in an automated way. So I think that the core is pretty much not done. It does what I wanted to do at the beginning. So I don't forecast many big changes there. Certainly some performance improvement, a little changes here and there, and adding more publishers. But where I see the focus of shifting is what to do with the data that is being captured. So it is already super useful to switch from metrics to events-based. And if you use Elasticsearch, you're going to see amazing advantages to go, the ability to dig down and see the actual data when you have a problem. This is going to give you already so much advantage, but I want to do more. What I want to do is, like, for instance, things like multivariate testing automatically. So we say that we have a latency distribution, and we saw at the beginning the latency distribution, they are not normal distribution, they are gamma distributions with a long tail. But so one thing that you can do is actually applying the central limit theorem to the gamma distribution and do some random sampling with a statistical process. And when you end up there, by the virtue of the central limit theorem, you are guaranteed to have a normal distribution. Once you have a normal distribution, what you can do? Well, you can do use things like student t-test or chi-square test to do comparison. So what if I deploy a new version and I was meant to see, so I was meant to observe a performance improvement. Now I have two distributions. So is the blue distribution better or worse than the other one? Yeah, okay, the other one has got a median around 12. This one around 20 something. So I would say that the purple one was better. Okay, what about this? Okay, now it's getting close. What about this? Which one is better? So one is got a smaller standard deviation. The other one has got a bigger standard deviation, but the median is slightly better. So which one is better between these two? So just judging by height is like what is called the eyeball statistics. This is not good, but you can use like we said, the student t-test, and make an hypothesis. The hypothesis is that the two curves, they are the same, and then using the student test, determine whether your hypothesis is nullified or not, or is valid. If you have a statistical significance that tells you what this is true or false. So I can use this because I have all the data, I have the raw data, and I have full information there. So I can use this to make a library to automate my deployment process. So my deployment process can become fully automated, and I can do multivariate testing on every commit and see if my new version is better or worse than the previous one. Anomaly detection. Wouldn't it be nice if you had the state-of-the-art machine learning to actually use it on top of the raw data? So there are companies that do this already, yeah. But you have to pay quite a bit of money, and the data, once you send to them, you're never going to see it again. They are meant to just to ingest the data and not for you to get the data back very easily. So instead, if you use mulog, the data is yours. You can store it, you can analyze it, you can apply numerical methods, you can do whatever you want. Why not get some statistical information or machine learning that tells me about anomalies detection? It not only tell me that there is an anomaly, it's going to go and tell me which data causes the anomaly, which requests. That would be amazing, isn't it? Wouldn't it be better if I could actually do this, select 2 time ranges and get in which request they are accountable for the difference? That would be amazing. That would be really good. So I could use something like the PCA, the principal component analysis. It will decompose the variation across a number of dimensions, and then tell me which one the dimensions are most significant on the variation of the data. So I could use that one. I could use like autoencoders, do encoding on one side and decoding on the other side, and then see which data is not explained by the encoded and decoded. So there is machine learning statistical method that can be used to do all these things. What I want to do in the next few months is start working on this type of libraries, make it open source so that you can use it the way you want it in your infrastructure, just to power the things that you need. And you have the raw data to do it. You can store the data. You can do it retrospectively. You can do whatever you want. And so if you have any knowledge about machine learning or statistics and you feel like you want to help, get in touch with me. There is plenty of work, interesting work to do there. So mulog is open sourced. Wrap it there. It's available. If you have any question, you can open an issue there. You can do, there is a discussion threads as well. If you have any problems, just let me know.